go 39 years back. What you see on this picture is the so-called Long Duration Exposure Facility, LDEF, that was launched by astronauts from a space shuttle in 1984 and was put into space as one of the most simple satellites you can imagine. It's basically an experiment carrier, which has nothing inside basically, but just all the different stuff outside, which are different panels that contain experiments on materials like electronics and solar panels, but also impact detectors, just to study the effects that the environment out there has on spacecraft and space hardware. And so this was put into space 1984, supposed to stay there for 1 year, and then the space shuttle would come and recover it again. Just a very interesting and intricate operation, especially in our context today when we talk about removing debris again. So this was one of the methods that today is also the most recommended one. When something is out there and you don't need it any longer, you retrieve it and bring it back to ground. But then some delays happened, and we all remember also there was the Challenger catastrophe in 1986. So this made LDEF actually stay longer than 1 year. It stayed in orbit for almost 6 years and was then supposed to even decay already into Earth's atmosphere and burn up there. And NASA managed to bring up a space shuttle mission again with a couple of astronauts to go up there and save this important piece of information and bring it back to Earth before it would burn up in atmosphere and destroy 6 years of knowledge that we acquired basically while this platform was up there. Now, a lot of people learned about how materials behave in space. For instance, I talked recently to a professor, and he confirmed that LDEF, even today, is still the major source of information when it comes to materials and how they degrade in space, for instance, due to extreme ultraviolet or atomic oxygen. But for us in the space debris world, this was also an equally important source of information, because what we were able to do with many of the panels that were on board of LDEF, we were basically able to take them and start counting impact craters there to study the space debris environment, which is way too small to be seen. And what was even more interesting is that we could relate the impacts that we had on those surfaces of LDEF to actual spaceflight activity. On the pictures on the right, you see astronauts recovering 2 satellites. And these are the satellites Vestar 6 and Palapa B2, which failed in 1984. They were supposed to go to a geostationary orbits as telecommunication satellites, but they got stranded in low Earth orbit, where they were basically released from the space shuttle, and they would be using a perigee kick motor to go into a higher orbit. But this burn failed, and so they got stranded. Now, they were insured, and the insurance company, they had to pay a lot of money, but they were also happy that they could make a deal with NASA, that NASA would send another space shuttle, recover those satellites, then they would refurbish them on ground and launch them again. This was basically recycling or reusing already done in 1984, which is quite interesting. In our case, what was even more interesting is when you look to the graph on the left, when we recovered LDEF, we saw very nice so-called maze swarms here, which were impact features that you probably wouldn't expect if you would assume that space debris is like randomly distributed out there. For meteoroids, this might be even the case, but we saw clear signals in the impact data. And this is for one panel of the so-called interplanetary dust experiment, which was able to pinpoint, to time tag basically the impacts that happened over the course of 2 or 3 months that you see in this plot, from April 7, 1984 to about July. And what we saw there were a lot of impacts. And later, what we did then was to model the solid rocket motor firings of these 2 satellites, Vestar 6 and Palapa B2, in our computer model. And we saw that when we modeled these firings correctly, that we could basically reproduce those impact signatures that happen on LDEF. So there were slag and dust particles that came out of the solid rocket motor that were orbiting then and then impacting on LDEF. So this was direct interference, let's say, of one mission to another. And then we had a scientist who continued this work, and he looked at other impact signatures that you see here. So these bigger clouds on the left plot, you see, we could relate them to Vestar 6 and Palapa B2, but there were still clusters that were unexplainable. And it was interesting when Donald Kessler, whom you know from the Kessler syndrome perhaps, was in Darmstadt for the 2017 Space Debris Conference. And he was saying how puzzled NASA scientists were when they recovered LDIF and saw these clusters of impacts which they couldn't explain. It was only in the early 2000s when we sat down and looked at another valuable source and spaceflight activity, which were so-called Soviet photo reconnaissance satellite retro firings. The Soviets basically recovered photographs they put on film, and then they were put in a capsule on board the satellite, and this capsule fired a solid rocket motor, and then it basically re-entered and was recovered on ground. They developed the pictures, and then it had the pictures. So this is analog photography from space. And we could model hundreds of these solid rocket motor firings. As you see on the right graph, we knew how they would have to re-enter so that they can be recovered over Soviet territory. So each point on that graph is one of the retro firings. Depending on which kind of system they use, they happened on a different position along the orbit. But even more interesting, to validate our hypothesis that the Soviets were doing this, and also to validate our model of the presumed rocket motors that they were using, we tried to correlate this with the firing, with the impact clusters that we saw on LDIF. And you see now on the left for the different Cosmos 1551, 5057, and so on, that this was quite a success story. So we were able basically to explain all the clusters that we saw on the LDIF panel, which was quite intriguing results. This helped us in return to validate the solid rocket motor model that we are now very confident with, that we use in our space debris model. This is helping us, especially if you're ever wondering for the small debris environment that is way too small to be seen, to actually know how much is there, to estimate how much must be there, just by knowing, for instance, in this case, how many solid rocket motor firings took place. And we know this from space history, that there were more than 2,400 of such firings. You see on the right a picture of how these motors look like. And what they do is they use aluminum powder to stabilize the combustion. But as soon as this starts burning, the aluminum reacts to aluminum oxide, and this can form slag particles, especially if you have designs where you have a nozzle cavity, as shown here on the right, where the slag particles accumulate during the burn process. And as soon as the burn is over, they basically are released slowly through the nozzle and exit into the vacuum of space. These particles can reach sizes up to 3 centimeters. It's way too small to be seen from ground. But we know that they must be out there because we had laboratory experiments, and there were also dedicated measurements basically to see these firings that happen in low Earth orbit with radars, for instance, and they were tracking these particles. Now, this is one example how space debris is generated. I cannot talk about all of them, but I wanted to give you an example of how small debris is generated and how our understanding evolves around what must be out there. For the larger debris, we can see it from ground, and one major contribution, or the major contribution, are explosive breakups. But we also have some collisions, and some of them happen also deliberately, like military experiments, also known as anti-satellite tests. One of the most detrimental one, environmentally wise, happened in 2007, when the Chinese military decided to shoot down their own weather satellite to demonstrate they have these capabilities. And they basically intercepted that decommissioned weather satellite with a kinetic kill weapon. It's basically just a projectile you put into the way of the satellite, and it crashes into it with its orbital speed, which might be about 7.5 kilometers per second. So it was shattered into pieces, and back then in 2007 increased the catalog of known objects by just 25% through this single event. Everything larger than 10 centimeters are objects we see, and right now the catalog has 3,400 objects about from this single experiment, of which I think there's still 2,700 up in orbit even now, 15 to 16 years later. And we can run experiments. Coincidentally, we had one planned with the IceCat sensor network in Scandinavia. They are running experiments on ionospheric scattering. And as a byproduct, they also receive space debris detections. And they were running it in March 2007. So it was shortly after the event. And what we were seeing there were also distinct signals of this Feng-Yun 1C debris cloud that was passing over the antennas. And then we are also able to basically put our model, which is called here Proof. Proof is basically modeling the antennas of IceCat in this case. And then it takes our master model, which has all the debris events that we model, like solid rocket motor firings. In this case, we modeled the anti-satellite test. And then we try to see whether our observations match with what our model predicts. And if not, we start basically calibrating to make numbers match. Now, if we put everything together, all the different sources, and I unfortunately don't have the time to talk about all of them here, but just to give you one example, then we come up with these pictures and these numbers you often hear about, like how much debris is there larger than 1 centimeter, and we speak about 1 million objects that could be right now up there in orbit. So 1 million is a very high number, and like 980,000 of them are not even cataloged, and maybe we will never see them even. Out of those, cataloged are 27,000, and now we can further break this down to numbers that you might be very familiar with, because this is the cataloged objects that we hear quite often about. About half of them are fragments from explosions and collisions. So these are the two major contributors here. Those 2,800 Feng Yun fragments, for instance, count into there. But we also see, and we come to this trends later, that there's already a substantial share of active satellites also. So this is a bit changing the environment of how we operate in space, especially when we come to talk about collision avoidance statistics that I will show you shortly. Now, when we talk about debris, we also have to ask ourselves what is actually the problem about space debris. And there's, you can look at different size categories. Now, this is a log-log plot that engineers love to look at. So we have a logarithmic y-scale that shows you the number of debris versus on the x-axis, the diameter of the object. If you look at the bottom right, you see the tracked objects is really only the far right region of objects, and also the numbers corresponding to those objects larger than 10 centimeters, you see it's about 32,000. But what we also know from experiments and also simulations is that once something impacts in your satellite of that size, about the size of an apple, your satellite is basically destroyed entirely, depending of course where it hits. But usually this is what we say, a catastrophic collision. Some people also refer to it with that term. When we go to lower sizes of 1 centimeter, we see that mission termination is still very likely because the energy that those objects come with is still excessively high. And for most of the satellites, it basically means that you deposit a hand grenade into this very fragile structure of a satellite, and then you can imagine that a lot gets destroyed inside. But even if we go to smaller sizes, and there you see nice pictures, we also recovered solar panels where we counted craters and were able to further validate our models. Such impacts, they basically cause degradation of subsystems. For instance, if your antenna has a hole or your solar panel suffers impacts, you see that this area basically is not any longer usable to generate power, for instance. Now, if we talk about avoiding risk that comes with space debris, especially the impact risk, we often talk about collision avoidance. And there's only a certain share of risk that we mitigate if our goal is to mitigate the risk for the mission terminating objects, because we might design against those that do not harm our satellite, that may degrade it over time, which is acceptable. But once an impact reaches enough energy to just destroy our satellites, we might not be any longer happy with just accepting that risk. So with the instruments that we use on ground-based radars, ground-based telescopes, we are able to basically track all objects larger than 10 centimeters, as just said. But these 10 centimeters make up about only 10% of the risk that for our mission we would like to mitigate. So no matter how many satellites you put on ground today, and no matter how many maneuvers you plan for your satellite to avoid potential conjunctions, you will always be able only to reduce about 10 to 20% of the mission terminating risk that is out there. In this picture, we see a Sentinel-2 satellite, and we can compute the likelihood of a 1 centimeter impact for the satellite over 10 years. And with the current space debris environment out there, the satellite basically has a 6% mission terminating risk, and we cannot do anything about it. Even if we have collision avoidance in place, it would be slightly higher, like 10% higher, if we wouldn't do collision avoidance. Now that these objects do cause damage, we saw clearly on our own mission in 2016 Our satellite Sentinel-1A at ESA suffered an impact into its solar panel. On the left, you see the picture of an unharmed solar panel captured by the camera that we had on board to monitor the proper deployment of this novel technology. And then we switched on the camera again 2 years later after we had that impact, and coincidentally it happened in an area that was in our field of view. So it was, so to say, one of the first selfies of basically such impact damage. Our satellite lost 5 to 10% of power permanently. You see this also slightly in the different shade of color that the solar panel element has. And this was caused, and we could do the analysis because the spacecraft was still alive. It was giving us telemetry. We could measure the attitude change due to that impact that happened, the orbit change, and we could basically then reverse engineer what must have impacted there. This impact feature is about 40 centimeters in size and must have been caused by an object of about 1 centimeter in size. So a space debris object 1 centimeter in size, too small to be seen for us, and indeed it was never, there was never any warning for any impact in that time. So coming to today's environment, if we look at this plot, and we are upcoming with an update of the space environment report very soon. So this is from basically showing you already, or giving you a preview of what will be in there. For some of the plots, others are not that far yet. But what we see in this plot or in this graph basically is that the environment is clearly growing in terms of, if we count the objects. Sorry. What we also see is since a couple of years that you have this category with the rather white color there, which are the unidentifiable objects. So they are partly due to improved sensor capabilities, which is interesting, that because you put up much more sensitive sensors and suddenly you start seeing more. Has it always been there? Has it been recently added? We cannot tell this for sure for many of those objects. But also we see that breakups still happen. And then after some time, you might not even be able to attribute the objects that you start seeing suddenly to events that happened in the past. But what we clearly see is basically that there's more than we thought there would be. And this is a bit worrisome. Especially what we see, and from looking at the space debris perspective, what is also of strong concern is the increase in the launch traffic that we had over the past few years. Essentially, already in the early 2010s, or even before the 2010s, many scientists, not only groups at ESA, but also others, were doing long-term simulation. We'll come to this to try to assess how the space debris environment will evolve. But we looked even at no further launch scenarios, which showed us that the space debris environment will grow even if we don't add anything to it. Now, exactly the opposite basically happened just a few years later with the new space paradigm. Suddenly we started to launch more and more. And these are predominantly constellation satellites. We know OneWeb, for instance, and Starlink are the constellations that are already quite successfully put in space in higher numbers and being operated. So we expect actually this trend to continue, and many more launches over the next few years from the space debris environment. This comes with a certain risks, of course, and it's our job to look at those. And one thing I wanted to highlight for you is how basically our approach to collision avoidance changed over the past few years. On the bottom right, you see a graph for the years 2015 and 2023. It's coincidentally exactly the time I had been at ESA also and doing collision avoidance, so I can speak here from my own experience, that for the first 4 to 5 years, we were basically not noticing any collisions or close approaches with constellation satellites. Mostly what we were seeing, almost in 50% of our collisions that we had to avoid or possible conjunctions, we had fragments from the Cosmos Iridium collision that happened in 2009, or the Fengyan 1C anti-satellite test that I talked about earlier. So those are the light blue bars that you also see in this bar chart. But then comes the dark blue one, which kicks in basically in 2019, 2020, and now it's basically dominating the scene here for the ESA satellites, and these are constellation satellites. What this means for us is that we can no longer safely assume in the larger majority of our close approach that we just perform a collision avoidance maneuver, because now we basically have to start watch out for who is actually operating that satellite that we have And this happens in more and more situations. So it means we always have to reach out to the other operators and see whether we can exchange orbits to coordinate who does the maneuver and in which direction, so that we don't produce or do a mistake together. What we also see is that in certain orbital regions, this is clearly the case. So if you look at the left plot, we see the number of cataloged objects and active payloads. And you can basically relate that in an orbit where you would go to to 525 kilometers, for instance. This is clearly the orbit of the Starlink satellites. So if you have a satellite out there, you will always encounter Starlink satellites. If you go to an 800-kilometer orbit, you will basically see no active payloads at all, or very rarely, and mostly encounter space debris objects. So it also depends where you put your satellite, and then you have to think, what will be my collision avoidance plan? I go to 520 kilometers, so I'm mostly encountering other operators. So I have somehow to take provisions to deal with this. Or I go to another orbit where there's almost no operators, then my collision avoidance actions will look quite differently. And now I come to the chart that I basically mentioned earlier about the future evolution of the space debris environment. And we are running these simulations on our side, and this is basically one plot that is currently being updated for the upcoming environment report. What we see here is extrapolations that we are doing of our current behavior. So the reddish lines are basically extrapolations that we did in 2005, 2014, 2021, and 2022. The lighter the color gets, the later we started the simulation. So you see actually that our behavior didn't get better, so to say. So the trend gets even worse if we come from 2005 or 2014 to 2022 and then project this into the future. What's even more worrisome is if you look at the blue plots, which are basically the no further launches scenario. At the beginning of this millennium, if you look at the 2005 one, we basically saw that if we would stop spaceflight activity, we would have a slowly increasing trend still, but maybe this is something very acceptable. But over the past few years, we saw if we added these simulations later and later, just because we started launching more and more, the no further launches scenario also starts to show a steeper gradient than before. So it gets more and more expensive, basically on this scenario, even the further we get and the longer we wait to take preventive measures. One thing to share as good news, but here also we have to see what the numbers for 2022 will say. We haven't still consolidated them, but on this plot, you basically see for the low Earth orbit how well the compliance is with space debris mitigation guidelines when it comes to post-mission disposal. What the guidelines recommend is that we achieve at least 90% post-mission disposal in low Earth orbit. You see, for instance, in 2021, for the global fleet of satellites in LEO, we had successful attempts, almost reaching 80%. If you also count the unsuccessful ones, you see we are almost there in reaching 90%. And what we also see in this graph is basically that the trend is slowly but surely increasing, which is good news. But we also have to ask ourselves the question whether this is enough. Studies suggest that if there are large constellations out there, again, like Starlink or OneWeb or others that are being added right now, we see in those studies that those constellations have to adhere to post-mission disposal in ratios much higher than 90%, show reliability even 99% or even higher. And we don't even know if this is technically possible, but this remains to be seen. But finally, what is also driving the environment, and this is unfortunately still a source of debris that we cannot somehow handle, is breakups that keep happening on orbit. And one recent one here, just to show you an example, it just happened last week. An Orbcomm FM36 satellite from the late 90s, but it was still in orbit, fragmented in 800 kilometers altitude. The fragments from that breakup, they basically remain up there, maybe for centuries. And others break up too, and this you see on this slide here on the left on the graph. We basically see that there's still about 5 breakups that we see per year happening, and contributing to the space debris environment. As rocket stages that explode that haven't been passivated, for instance, or satellites where we sometimes don't even know what happened. Maybe they collided with something and then the breakup cloud is generated. But we don't see at the moment that this trend is declining, and this is basically also what is driving the environment evolution that I've shown you on the plot earlier. Now, finally, to conclude my talk, maybe also to end on a personal note right here. We have talked about exploration, but what I also found quite interesting when I look at exploration is how much we actually learned about our own planet. And the astronauts that went out there, it's sometimes interesting to listen to their stories and see how when they're out in space, they actually turn around and look at the Earth rather than away from it, and see that how fragile it is. And maybe also see that out there, and this is what missions have confirmed when we went to Mars or Moon, how hostile the whole world around us actually is, and that there's this one habitat that we all share together. And I like the story because it maybe also gives us an idea of which missions we maybe need to put up to protect what we value, and which others we maybe cannot launch because we are running out of space capacity up there. And this is maybe a good starting point to get into such conversations, seeing that it's getting more and more crowded and we need to do something about it. I like to end with a quote by Carl Safina, which I personally like a lot, which captures it very well. It says, "Beyond our planet lie only facts, but all meaning resides here." And with this, I would like to end my talk and